Welcome. Today, we're diving into the world of counter applications. Counters are essential digital logic components, and we're going to explore some of their key uses. We will discuss frequency division, which involves clock signal division and frequency scaling. Next, we'll look at timing control, which enables precise timing sequences and delays. Finally, we will explore control systems, focusing on sequential logic and state machines. So, what exactly are counters? Counters are sequential logic circuits that count clock pulses and produce binary output sequences. They have several key features. They use memory elements called flip-flops. Their operation is clock-driven. They progress through binary states and they can operate synchronously or asynchronously. Let's start with frequency division. Frequency division involves reducing the input clock frequency by a specific factor using counter outputs. The formula for frequency division is F out equals Fn divided by 2 to the power of n. In this formula, F out is the output frequency, Fn is the input frequency, and n is the number of counter stages or flip-flops. Consider these examples of division. A 2-bit counter divides the frequency by 4. A 3-bit counter divides the frequency by 8. A 4-bit counter divides the frequency by 16. Here's an example of a simple frequency divider circuit using Verilog code. This is a 2-bit counter, which divides the frequency by 4. The module is named Frequency Divider 4. It takes clock and reset as inputs and provides divided clock as output. The counter is a 2-bit register. On every positive edge of the clock or reset, if reset is asserted, the counter is reset to 0, 0. Otherwise, the counter increments. The output clock is simply the most significant bit of the counter. Hence, the output frequency equals the input frequency divided by 4. Now let's examine timing applications. Counters can generate precise time delays and control timing sequences in digital systems. Some common uses include digital clocks and timers, pulse width generation, delay circuits, and real-time control systems. Let's look at timer circuit implementation, which creates a 10-second timer using a 1 MHz clock. The module is named timer 10 seconds. It takes clock and start signal as inputs and outputs a timeout signal. A 24-bit counter is used. The maximum count is set to 10 million, that is 10 times 1 million. On every positive edge of the clock, if the start signal is not asserted, the counter is reset to 0 and timeout is set to 0. When the counter reaches the maximum count, the timeout signal is asserted. Otherwise, the counter increments. The counter counts to 10 million to create a 10-second delay. Next, we have control applications. Counters play a crucial role in managing step-by-step operations and state transitions in digital systems. Examples include traffic light controllers, washing machine cycles, address generation, and state machine sequencing. Here's an example of a traffic light controller implemented as a state-based control system. The module is named Traffic Controller. It takes clock and reset as inputs. The output is a 3-bit signal called lights, representing red, yellow, and green lights. A 2-bit register is used to represent the state, and a 4-bit register called timer is used to control the duration of each state. On every positive edge of the clock, if reset is asserted, the state and timer are reset to 0. Otherwise, if the timer is 0, the state is increment and timer is set to 8 if the current state is 0, otherwise timer is set to 4. If the timer is not 0, the timer is decrement. Thus, the counter controls timing between traffic light states. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.